he awarded PhD from IIT Kharagpur, and he has the research area. His research area is VLSI architecture design, VLSI signal processing, VLSI design, hardware design methodology, FPGA-based system design, CORDIC. So today we hope it's a very wonderful session. So thank you, sir.
BTech students and two, three MTech students. They works basically on the edge computing system. We works on the RISC-V based edge computing systems, particularly for the end node when the energy constraints is a big issue. We are working. Basically, we are working for the forest applications. Recently, we have fabricated one indigenous processor on the RISC-V. Another domain like my students are working, that is VLSI for the communication systems. That is basically for the. So I thought I had a plan to talk about edge computing systems, but sometimes later I will talk. So I decided, okay, will it go with the VLSI signal processing? My old research domain, even if it's current also, I am working on that particular domain. As he told that the theme is approximate technique. Nowadays, approximate technique is evolving like anything. Here they have chosen very recent theme. Basically, this is useful for the highly computational need and high data bandwidth applications, and particular the computer arithmetics. So basically approximate, though it has a application to the main basic building block is your computer arithmetic. And to my understanding, just I explore you and I will come to my topic where I am using the similar approximate arithmetic for the signal processing applications. So basically, if you talk about the approximate arithmetic, it has a very domain-specific applications. So, for example, if you go for the image compressions, okay, image compressions or video transmissions, where you need a very expensive algorithms to be implemented on a hardware, either in FPGA or ASIC, where you need a multiplications, divisions. Sometimes you need the transcendental functions like exponential. So if you go these transcendental functions like either linear functions like multiplication and division, or transcendental functions like hyperbolic or exponential functions, then you need a high resolution, high uh, bit size of your computer arithmetic. Okay, that bit size will be increased. Suppose, for example, if you look at 8-bit operand, then output you will look. No, I will share the slide. Just I am introducing, and I will come to my slides. If you look at the computer arithmetic, then a 8 cross 8 bit. Hello. Hello.
Yes, sir. Yes, sir.
Uh,
Audible, sir. No problem.
when it is muted?
No, sir. I
Just
think
now
somehow
muted or?
This is for
just
participant. Actually,
words.
Professor Roy, it is for two
Huh.
participant. They are not muted themselves.
No, mine also is muted.
Yes,
Was
sir.
I?
Yes, sir. Because I am using mute all, na. That's why.
Oh, okay,
Again,
okay. Okay. So, so that multiplication and divisions, the bit size increases if for a particular application, for particular operations. One operations, thus bit size increases 2n, right? So n bit, if you talk about operand in the multiplication side, it will go to the 2n. So if you go for the next stage, it will go 2n, 2n, 4n. So it is very expensive to support these hardwares to give the 100% accuracy. So we have to truncate. You have to those bits. Otherwise you have to use other alternative method so that you can approximate, and so that your bit size, bit resolution will be decrease, so that you can decrease your hardware size, and you can you obviously have to sacrifice with your accuracy. So it is a trade-off between the, if you talk about the approximate or arithmetic or approximate arithmetic, then it is a trade-off between the hardware cost and with your accuracy. So if you go to the bit, even if you, these things also it is there, and if you go by the integer integer operations or floating point, again the issues are there, but that issue is very manageable. That issue is very manageable, and you have to get your you know minimal hardware. You can get minimum, like minimum less uh, error prone, okay, error prone, and you can get good results out of that. But sometimes, if you go to the, as I told, the compression, where the accuracy is not big issue, accuracy is not a big issue, then probably approximate technique is a very adaptable, very acceptable to implement to minimize your hardware. So that is the main theme of your approximate arithmetic, which is used for the very domain specific application, as I told, video compression and transmissions. One example, many examples you will get it, maybe other uh, resource person speakers might have exposure to you regarding the approximate arithmetic and its applications. But to my, as I given that main title, let me share it, my screen applications. Let me share first, okay. Is it visible, my slides?
It's going, yes, sir, visible.
Okay, so so coming to the my topic, today's topic, what I have chosen, CORDIC-based VLSI architectures for real-time spectrum analysis. So I have chosen because time is very small, like minimum time it is they have given. So I have chosen very domain specific real-time spectrum analysis. So I will introduce the spectrum analysis, introduction to the spectral analysis or spectrum analyzer, and then I will introduce the different methods or different blocks is used for the real-time spectrum analysis, and how to implement in the hardware. There are very classical MAC-based approaches are there, multiply and accumulate based approaches are there, ROM-based approaches are there. But I will talk as an alternative architecture to this conventional architecture, that is a CORDIC-based architecture for the real-time spectrum analysis. So I will introduce the CORDIC architecture first, then I will go to the uh, different architectures, which different blocks which are used for the spectrum analyzer or for the real-time spectrum analysis. What is the design aspects? What is the design methods? And what is the implementation methods? And what are the challenges? That I will discuss. And out of this main talk, since students and the faculties are there in the audience, so I have given very static, very fundamental stops to the application side. I have gone. I have prepared my slides from basics to the some moderate design. So it will, I hope it will help all to teach in your subjects, to incorporate some of the topic out of this to your subjects who are teaching the VLSI architectures. And also I will give some research directions on this particular topic so that you can carry forward your research on this. So let me go to the next slides. Yeah, this is my outlines, what I will talk about, the I will introduction on the spectrum analysis, and I will talk about CORDIC, an algorithm and architectural design aspects of your CORDIC, and then I will talk about one of the building block for the spectrum analysis, that is called a windowing functions. And my architectural point of it is a I will discuss about algorithms and functions of the windowing, and then I will talk about the two windowing architectures which we have developed and published also. And running DFT which is uh, bit away from your general FFT based architectures. I will talk about the running DFT architecture. I will talk about its advantages and limitations. So this way we will go the three topics we will discuss in within these 2 hours. And if you have any doubts, you can message me, or I will give you. I supposed to have an interactive session. You could ask in the between, but since your host is muted, you may not ask me on the line, but you can uh, raise your hand. I think they will open up. Otherwise, you just note down your questions, and at the end we will discuss the whatever you have doubt. I will try my best to clear your doubts. So will start the introductions. When we were talking the real-time spectrum analyzer. So what is a spectrum analyzer or spectrum analysis? That it converts your time domain signal to it transforms. It converts or it transforms the time domain signals to the either time scale or time frequency domain signals. Okay, time scale or time frequency domain signals, or purely frequency domain signal, right? So it is, what is the advantage of all of you know from the digital signal processing basic, that it is easier to analyze the frequency domain if you take the frequency domain component, and also it will be used to compress the data, and it will help you to store so that your memory bandwidth will increase. It is not only for the analysis, also it will can be used for the synthesis process, right? So I will talk about the particular analysis part. So there are many methods to transform time domain signal to the time scale or time frequency domain signal. Those are called Fourier transform, and another is called a Mellin transform. Basically, Fourier transform, Mellin transform is used to transform from the time domain signal to the frequency domain signal. And my cursor is visible, Mansa or
Yes,
Satisha?
sir, it is visible.
Yes, yes, visible, sir.
My cursor.
Yes,
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 sir, cursor
visible.
is visible.
Okay, okay. So then another is called, everybody knows, overlay transform, that converts your time domain signal to the scale domain signal. Overlay transform, it is being used. And another is a empirical mode decompositions. So basically empirical mode decomposition, it will convert time domain signal to the frequency domain, but it will be helpful to when the signal is a time invariant. Okay, time invariant signals, the EMD empirical mode decomposition or variable mode decomposition methods are being used, which will convert your time invariant signal to the frequency domain signal. So basically Fourier transform, Mellin transform being used to domain periodic signal, and time invariant signal. It is time invariant and periodic signal. It is used for Fourier transform, Mellin transform, and but whereas the EMD and VMD, empirical mode decomposition and variable mode decompositions, it is used for the time variant signal, and aperiodic signal, time variant signal. It will use for the EMD and VMD being used. Similarly, another popular transform which is recently has come up, that is called a Stockwell transform. Uh, the Stockwell transform, it represents your transforms your time domain signal and represent your signal both time and frequency. So when it happens that when it will converts time domain to the frequency domain signal, most of the time information we miss on the after the transformations. So which will be retained both time information and frequency domain information in the transformation domain. Then Stockwell transform is a very useful. So so we work on all these domains, but all these many transfer methods are there, but we work on particular in this domain: Fourier transform, Mellin transform, Oberle transform, empirical mode decomposition, variable mode decompositions, and Stockwell transforms. We work. Recently, we have we have worked very good. One of the research scholar. He is a Prithviranjan Khatwa. He has worked on the complex wavelet transform. Complex wavelet transform. We have given a new algorithms and to reduce the hardware. That is our motto was there. So we have done it, and the Stockwell transform. We are developing our architecture and we are applying to the biomedical signal processing, particularly the ECG. But we will not go to there. I will come to the very basic transform, that is called a Fourier transform, which is used for the in a digital domain. If you go to the digital computation of your Fourier transform, then we use the DFT, discrete Fourier transform, and obviously it's a first algorithm that is known as a first Fourier transform. Basically convert your time domain signal to the frequency domain signal. So if you come to the typical spectrum analyzer block, so if you are using the FFT method for the converting time domains to the frequency domain signal, I have not written here frequency domain side. What is happening here when you analog signal, you take it and you do the sample and hold and data, particularly the data acquisition systems, when you will convert your data from your analog to the digital and give to the spectrum analyzer, particularly FFT. Then FFT will take, all of us know that FFT algorithm, it will work for endpoint FFT, so it will take n number of inputs and it will give the n number of frequency component, right? So particularly if you implement on the your butterfly structure of your FFT, so basically it works on the blocks of data. It needs the blocks of data, and so that it will keep on processing using your FFT algorithms, and it will give the frequency component at the other end. So when it will take this block of data, then you will see that there will be an issue of spectrum frequency component side. There will be a spectral leakage. Because if you take the direct truncation of data, set of data you are truncating from a data series, then if you go to the FFT side, then you will give the spectral leakage. So to minimize this spectral leakage, what is the spectral leakage? Now spectral leakage is that, say for example, you take a 50 Hz signal, right? If you give only one 50 Hz signal, then if you convert through the FFT Fourier transform, then you will, in the frequency domain, you will get one peak at the 50 Hz frequency component. If you look at x-axis is your frequency domain, and if y-axis is your amplitude, then one peak you will get at 50 Hz. Now other frequency components, say 1, 2, 3, 4, 5, or 50, or that side 50 and 52, you will get 0, 0, 0 in the ideal case. But it's supposed to get it, but if you go with the direct truncation, it means you are using the rectangular window for that, then you will get frequency components. You will not get a peak at one place, rather you will get one peak, maximum peak you will get it in the other side. Frequency components, say 49, 49, 48, 47, 46, 45. Then other side, you will go to the 51, 50, 53. Some amplitudes you will get it other components also instead of 0. So what is happening here, that some of the spectrums are getting leaked from your main component to the other components. So that is called spectral leakage. Sometimes if you have a various number of frequency component in your signal, maybe one of the component will affect your another component, and where the amplitude goes increasing. So which is supposed to be filter it out, but that will come up. So this type of issues will come because that due to this spectral leakage. So to minimize this spectral leakage, we will get the windowing functions. There are so many windowing functions. You will get it: humming window, Blackman window. There are so many windowing. We will discuss it here. So what it does by rather than truncating your data, what it do, like you make the windowing so that it will not directly truncate your data. It will smooth your data so that it will minimize your spectrum, minimize the spectral leakage at the output side. So these windowing functions, either you can in the time domain or you can do also in the frequency domain. I mean, take your time domain signal, do the FFT, then equivalent, take the what is the time domain frequency window functions, take its frequency domain window functions and multiply it. Okay, so that you can get the same result, so that at the output side you will get the minimum spectral leakage. Spectral leakage cannot be zero, but it can be minimized using these windowing functions. So this windowing process you can do at the time domain as well as also in the frequency domain. So but I will talk about the time domain side. Let's will go. Yes. So what we will talk whether this windowing functions and the either this FFT or what I will talk about the moving DFT or running DFT. Those can be implemented with the conventional arithmetic, multiplier, ROM, and divider, all these stuffs, conventional hardware blocks. But I will talk about the CORDIC-based. Well, I will employ a special computer arithmetic block that is called a CORDIC, coordinate rotational digital computer, to implement or to design or implement these windowing functions, as well as the which I will give a new spectrum analyzer method that is called a running DFT. So since the basic building block is a CORDIC, that we will discuss first about the CORDIC. What is a CORDIC and what is its beauty, advantages, and what is its limitations. Also, we will discuss how to come up these limitations and how to apply or employ those CORDIC blocks to these windowing functions and running DFT. So that's what we will discuss now. So if you come to the CORDIC algorithm and architecture, this CORDIC, as I told that the abbreviation of the CORDIC. What is a CORDIC? That is a coordinate rotational digital computer, and short term it is called a CORDIC. CORDIC. Coordinate rotation digital digital computer. Okay, digital computer. So if you look at this computing, this is basically the computer arithmetic, specialized computer arithmetic, which will help to compute the trigonometric functions that sin theta, cos theta, and also hyperbolic functions like sin hyperbole x, cos hyperbole x, and linear functions like multiplications and divisions, linear CORDIC. So there are three type of CORDIC algorithms you will get it. That is called a circular CORDIC, which will help other trigonometric functions to compute the trigonometric functions, and hyperbolic CORDIC, which will help to compute the sin hyperbolic and the cos hyperbolic, and the linear CORDIC, basically it is used for the multiplication and divisions using the additions. So you see, if you look at the circular CORDIC, see, because conventional I have not written here, but if you go for the typically the trigonometric functions computations, or something, trigonometric values has to be computed and used for some processing for multiplications or divisions or kind of stuffs. So what generally do, we will take the pre-compute the sine values or cos values, trigonometric values, and store in a ROM, and get access to those ROM values and go for the further processing, addition, multiplication, whatever you require, right? So that's what we do. So if the number of points, like if the size, like number of size of the trigonometric values will increase, so your memory size will be increased. So it requires the large memory to be stored, and other end you have to need a multiplications. So multiplication is a very bottleneck to minimum. To it is it will has a very bottleneck in terms of timing performance, right? It takes a propagation delay of the multiplier is a very large, so it will restrict your throughput of your architecture, right? So generally, so that we can uh, uh, avoid the multiplication factor, we will avoid the memory large size, and we can do same things using the CORDIC in case of the trigonometric functions. Similarly, for the hyperbolic and of course for the linear also. So in a linear function, of course, we don't require a memory, but in transcendental functions, you obviously require the memory also. Not only to that, it will help the derivative of your these trigonometric functions and transcendental functions, and I will highlight some of them also. So if you come, though this is a very old, like this CORDIC first it is proposed in the by Volter in 1959, but it is a very useful architecture for the both signal processing and communication systems. So if you look at that, how the circular and hyperbolic linear CORDIC will differ, that how it works. But basically, this circular CORDIC, it is a rotational, and if you look at the quadrants, like this is circular, vector will rotate on the circular mode, and you have to compute your say vector is a vector rotation xi and yy, and you are rotating by alpha I, then it will rotate to a vector that is called xi plus 1 and yi plus 1. Okay, so vector will rotate in circular. Okay, so that's why it is called a circular CORDIC. And hyperbolic, if you if the vector rotates on the hyperbolic path, so then it is called hyperbolic CORDIC. And if your vector rotates linearly, this is the linearly dotted line, then it is called a linear CORDIC. But this, by using this different type of vector rotations, its functionality will change, its algorithm will change, and its application will be differ, right? So we'll go with one after one. Maybe I will talk about the circular CORDIC, generalized, then I will derive your generalized circular generalized CORDIC equations, and where I know how the hyperbolic and linear can be achieved out of that. So let will go details of the algorithm and architecture of the circular CORDIC. So here, as I told that it will rotate circularly. As I told that vector position v, x, and y, and new position after rotating your alpha, you will get v prime, x prime, and y prime. Then this is your target angle alpha. You are rotating alpha. So now our objective is to calculate if the original point is your v vector is x and y, then what should be the new vector v prime with your coordinate x prime and y prime after rotation of your alpha. We will compute the vector, and that is coordinate points x prime and y prime. Okay. So so to do that, what will happen, you see that if you look at this b, right, b, then you are rotating with alpha, this alpha, right? So assume that, so come to the right side, I will assume that there is an angle phi. Okay, there is angle phi. Phi is a phi is a known because vxy is known, so phi will be a known. But other side alpha is a known, but x prime y prime is unknown. So we have to compute the x prime and y prime. So by introducing your phi, say what is a phi? Phi is if you look at phi, then x is nothing but your r cos phi and y equal to r sin phi. X is your r cos phi and y equal to r sin phi. So phi you can you can get cos inverse of x by r. So that way you can see that xy is you can represent r cos phi and r sin phi. And if you look at it, will rotate to the v prime x prime y prime. What is your x prime? X prime will be your r, because this vector radius is the same. So radius r cos alpha plus phi, alpha plus phi. This, if you look at this x prime and this is your y prime, so then x prime and y prime will be your r. The projection I have taken, okay, projection of the coordinates I have taken. So x prime equal to r cos alpha. If you expand, it is r cos alpha cos phi minus sin alpha sin phi. So since x equal to r cos phi and y equal to r sin phi, if I put it here, then x prime you will get in terms of the xy, x cos alpha minus y sin alpha. Okay, and that is for the y prime also. That y prime you will get your x sin alpha minus y cos alpha, right? So these derivations, new equations, new coordinate, I got it in terms of your x prime y prime coordinate. That is my new coordinate. I can express in terms of my known coordinate x and y and known angle alpha, known angle alpha, rotation angle known rotation angle, that is your alpha. So in terms of I can express by this simple basic rotations. So if you come to the next slide, then I can represent these two equations. This one I can represent in the matrix form, that x prime y prime equal to cos alpha minus sin alpha cos alpha xy. So this is the matrix equation, matrix representation of your vector rotation. You can get it. Now what I will do the approximation, because though I know the alpha, but cos alpha I have to compute it, sin alpha I have to compute it, sin alpha and cos alpha I have to compute it, right? So how will I compute it, right? So these computations, what I do, like I will apply some approximations. What is my approximation here? To compute this kernel particular, because x y is a known to you, and x prime y prime is your my new vector, and alpha is a unknown, cause this kernel matrix is unknown. If alpha is known, of course this is known value, and you can store these values and you can do the computations. But when alpha is unknown, I mean, like alpha will be a variable, so it is not easy to get this very simplest way to get your this kernel matrix, right? Even if alpha is known, alpha is known and you do the vector rotations, so then what you will do it? So what you do, like that approximate, what I will do, assume that alpha, what I will rotate it. So rather than taking the v vector from xy coordinate to the v prime directly with the alpha, angle of alpha, what I approximate it, I will not do that. I will approximate that I will rotate my vector with some micro rotations, known micro rotations, so that I can make a to and fro, so that I can reach the v prime. So rather than going the one go at alpha, I will go with the different steps. So initially I will rotate this vector v, I will rotate with the alpha 0 angle. So alpha 0 is known to me. I will rotate alpha 0 to known to me, a particular known. What is alpha 0? I will talk about it. I will, this known angle, I will rotate it to this side. So this is my new vector positions after the rotations. Then after that, what I will do, because this has gone to the beyond my desired vector, so I will bring this vector, I will rotate back with the another angle alpha 1. So I will come back here with my alpha 1 angle. So alpha 1. Then I will again go to the alpha 2, alpha 3, alpha 4, alpha 5, like that I will go. Still you will get your alpha m minus 1. So after some micro rotations between known angles, I may reach to my desired vector location, or by very close to my desired vector locations. So this is the approximation I have to make it here. So instead of this alpha single angle alpha, I will break this alpha to a alpha 0, alpha 1, alpha 2, alpha ith rotations, and alpha -1. So this I have gained plus or minus means the rotation may be either side, na, this side or this side. If you go into that side, then you have to subtract it. Then this is this side, then you have to add it, subtract it, add it, subtract it, add it, subtract it, like that. Addition and subtraction you have to do for the each micro rotation, each known micro rotation. I'm talking about each known micro rotation, because alpha 0, alpha 1, alpha 2, alpha I, alpha -1 is a known micro rotation angles. Okay. And this if you add or subtract all as a resultant, you will get your angle alpha. Finally you will get your alpha, or close to your alpha you will get it. So this is the what assumptions I'm approximating here. If you look at R, like if you represent it the plus or minus signs, I will introduce my another variable called a di alpha I. Okay, alpha I is 0. No, these are 0, 1, 2, 3. I represent alpha I. So it is nothing but summation of di dot alpha I, where I varies from 0 to a -1. That alpha equal to, this is the summation, or this is the equations you will get it. See what is alpha I? Then you, as you told that what is your alpha I? But this is known angle, known micro rotation angle. So that is the approximation what I have taken here. The alpha I is nothing but 10 inverse 2 to the power minus I. Okay, where I equal to 0, 1, 2, 3, 4, like that. If you draw this I equal to 10 to the minus 10 to the minus I, if I equal 0th rotation, in the first rotation, if you say 10 inverse 2 minus, sorry, I equal to 0, 1, 2, 1. So you will get 2 to the power 0. How much you are getting? 1, right? You will get 1 and half, like that. You will get a half, 1/4 you will get it. So you will see that I will come that what are the angles you will known angles you will get it here. So here di is nothing but sine of residue angle of zi. So as I told that you have to rotate these macro rotations, and you have to see whether how much angle I am deviating from my your known angles. Okay, known vector positions. So that things I can calculate from here. This is my known micro rotation angles, and how much angle remaining to be rotated, either positive side or negative side. So depending upon the positive sign or negative sign of these computations, you have to decide the sign of your rotation, which go to the positive direction or negative directions. So d I have to, that is sign value, that plus or minus, you have to decide from this your residue angle. Residue angle means that your remaining angle to be rotated. Remaining angle to be rotated. So if you look at these representations, means that d of I, this sine bit is nothing of your sine of your residue angle zi, and which is your component 1, either 1 or -1. And here I, as I told, I will vary from the 0 to a -1, where m is an integer equal to your word length. That what the word length we have to take, that operand length, then that depends upon your that m that I will varies from the each rotation 0 to m minus, it will vary, and m is equal to your word length. You can rotate less or you can rotate more, but if you go to the more, no effect, and if you go to the less, then you will get your more error. So generally you take the number of iterations equal to your word length. Come to the here, what is the micro rotation angles alpha I? Say let what I have discussed, approximate angle I have, approximation angle I have taken here, known micro rotation angle I have approximated. So 0 iterations, if you do 10 inverse 2 to the minus 0, that is a 45 degree. So in the first iterations I have to, or that is 0th iterations, I have to rotate my vector by the 45 degree, and I will check whether I have what is the remaining angle. I have to check with my alpha whether it is a positive side or negative side. So like that I have to 45 degree. If you second iteration, that is first one iterations, that is 10 inverse to the minus 1, that is equivalent to 26.5651 degree. Okay, so that angle I can rotate. These are all my known angles, known micro rotation angles due to my these approximations. But approximations. Okay, so these angles are known angles. I can rotate my vector, and if you look at if I this micro rotations I'll add or all will be subtracted, this will be a it will be a minus 90 degree to the 99 degree. Okay, approximately minus 99 degree to the plus 99 degree. I can minimum 99 degree, left side you can go, other side you can go up to the 99 degree. So basically the vector you can rotate with a first quadrant and a fourth quadrant. Okay, first quadrant and fourth quadrant of your coordinates. So this is the limitation, that you can rotate your vector, you can compute your vector only within your first quadrant and fourth quadrant. It won't work for the third and fourth quadrant. Sorry, second and fourth quadrant. But there is a solution. I will give the solution for that also. But let's will go with the only how the it will compute with the first and the fourth quadrant. So here example I have given 30 degree for the how it works. Finally it will go to 45 degree, then subtract 26 degree, then add 14 degree, then subtract 7.12 degree, then add 3.5 degree, then add 1.7 degree, subtract 0.89 degree, then add 0.4 degree. So closely you will get 30.26 degree. So if this iteration will keep on increasing, say how many iterations I have taken? 1, 2, 3, 4, 5, 6, 7, 8. I have taken 8 iterations. So I have reached around my 30.2647. I supposed to reach to 30 degree, but I reached to the 30.2640. So 0.2647 degree errors are there. But if you can increase this number, increase this iteration number, then you will very close to you will get 30 degree, very close to the 30 degree you will get, so that you can minimize the error. Okay, so this what again the error versus your iterations. Okay, if you minimize the error, then your iterations has to be increased, so that you have to compromise your timing. Now come to the derivations, like how to have a your CORDIC algorithms, how will you derive that CORDIC algorithms. Again I'm starting from my generalized matrix, vector rotation matrix, this one, and where alpha equal to this one. So to compute this kernel matrix, what I do, like cos alpha minus sin alpha cos alpha, I will represent my alpha with my micro rotation angles, alpha 0, alpha 1, alpha 2, alpha m. So if I put it here, this expression, right side expressions here, then it becomes the cos of alpha 0 plus, if I talk plus or minus alpha 0 plus or minus alpha 1 plus or minus alpha 2, like that. Okay, so all cos term, sin term, all cos and sin terms you will get like this, right? So but here I will use the one of the additive property for the rotational matrix. If I put it, then this addition of your angles will be the multiplication of your matrices. Okay, that is called a additive property. You can just simply take cos alpha 1 plus alpha 2, sin alpha 1 plus alpha 2, sin alpha 1 plus alpha 2, cos alpha 1 plus alpha 2, just expand it, you will get cos alpha 1 sin minus sin alpha 1, sin alpha 1 cos alpha 1 multiply with cos alpha 2 minus sin alpha 2, sin alpha 2 cos alpha 2, like that you will get it. Okay, you will get it like this. Okay, so these two matrix multiplications, you will these two matrix multiply form, you will get it. Okay, so since I have been the m number of micro rotations, so I can get my m number of matrices to be multiplied. These are all known values. These are all my known values. So these kernels I will get it, and what I will do now, I will first this x y, this my known coordinate will be maybe multiply with the cos alpha 0 this matrix, then I will multiply with this matrix, then I will multiply with the next matrix, so on I will keep on, so that I can get my final coordinate value x prime and y prime. I can do that, right? But to make simplify, to get our iterative algorithm of your CORDIC, what I will do now, I will take my cos alpha 0 as common, cos alpha 0, cos alpha 1, cos alpha 2, up to the cos alpha minus 1. So if I take a common out of this, then I will, what I left with 1 minus plus 10 alpha 0, 1, sorry, plus or minus 10 alpha 0, 1. So like that I will get it. So if I take the each component cos alpha 0 cos term from my each matrix, then I will lead to this matrix, right? This lead to matrix having the 10 alpha 0, 10 alpha 1, right? So now 10 alpha 0, 10 alpha 1, 10 alpha I or 10 alpha minus 1 is known to you because of my approximations. What is that? That is 2 to the power minus I, isn't it? 10 alpha I, if you look at 10 alpha I, is nothing but your here 10 alpha I is nothing but 2 to the minus I. So I can replace this 2 to the minus I equal to 0, I1 to the minus I, like that I can put it. So I put my 10 components in terms of 2 to the power I. So this is the matrix I will get it, and if I do the iterative cos y x of x and y, if I multiply with this vector, say take a generalized form, okay, 1 plus minus plus 2 to the minus I plus or minus 2 to the minus I 1. So this is generalized matrix I will take it. If I multiply with, what will happen, x, this becomes the minus or plus 2 to the minus I yi, right? That's what. If a minus plus I talk about to di, plus or minus I take di, then it becomes the iterative equation xi plus 1 equal to xi di yi 2 to the minus I, and similarly yi plus 1, I will get my yi plus di xi 2 to the minus I. So from here you can see that if I will multiply my input vector with the first one, and what the resultant will come up with the second one, what is the resultant will I come up with the third one. So if I go last up to the my mth matrix, known matrix, then I will can get computation like this. I have to do the computation like this, okay. And at the end, when it reaches the m, x minus I1, xi plus 1 becomes your m, right? xm and ym, you can compute it. After the m minus 1 rotation, you will get I equal to m minus 1. If you put I equal to m minus 1, then it becomes the xm and ym. So final result, final coordinate, you will get it after this rotation. So as I told that, you see xi and yi and 2 to the power minus I, it is coming from the known vectors, right? Known input vectors. It is iterating, getting updated, and 2 to the minus I. No, it is just shifting, right? 2 to the minus I means yi has to be shifted by I bit, right? I bit. So these two vectors, these two equations you get from these equations, and to compute this di, how will you compute the di? Di can compute from the residue angle, right? Residue angle. So this residue angle, the expression which one I had given, that residue angle z of I equal to alpha I minus I r equal to 0 to r minus 1 alpha r, then that can be represented as z I plus 1 equal to z I minus or plus alpha I, because alpha is a known angle and zi will be your residue angle. So the previous residue angle and what should be the present residue angle, it will be your zi plus 1. Again, that will be used for the next one, and next micro rotation, known micro rotation angle. So that way you can get your residue angle. So depending upon the residue angle, either plus or minus, you can get your di, because di is nothing but your sine of your z of I. Okay, so that one you will get your di term. So if you go, this is the this is what I have written here. My iterative expression for my CORDIC. These are three equations, iterative equations, all together called a CORDIC algorithms. CORDIC iterative algorithm. CORDIC iterative algorithms. So these three equations I can use to design my hardware architecture, iterative architecture, which will compute my CORDIC operations, which will do my CORDIC operations. So if I go to the generalized, as I told, this is for the circular codic, I will introduce another term that is called eta. Okay, I will generate my eta. What is eta? Eta is a factor which will decide your circular codic or hyperbolic codic or linear codic. If eta equal to 1, and of course alpha I also, alpha I equal to, when eta equal to 1 and alpha I equal to 10 inverse 2 to the minus I, then it will lead to a circular codic. If alpha equal to minus 1, and eta equal to minus 1 and alpha I equal to 10 hyperbolic 10 hyperbolic inverse up to the minus I, then it will go to the hyperbolic codic. Okay, this eta and alpha I have to replace it. And if eta equal to 0 and alpha I equal to 2 to the minus I, which is linearly move, alpha equal to 2 to the minus I, then it is called your linear codic. It is called your linear codic iterative equations. So by changing eta and alpha I, you can get the rotation algorithms based on that is for the circular codic or linear codic or hyperbolic codic algorithms. So here di equal to, of course, it is a component either minus 1 or plus 1. As I told, that another term like here rotate, as I told, circular with it is there are two modes of operation. One is called a rotating mode and another is called a vectoring mode. What it means, that in the rotating mode is that x0, I mean initial coordinate is given to you, right? And theta will be given to, you have to rotate your vector by angle theta, and you have to calculate what is the resultant value of your xm and ym, or the resultant coordinate of your vector you have to calculate, means xm and ym you have to calculate it. So on that case, what you have to do, the rotational mode, what is that theta angle is given to you, then you have to make the theta angle to the 0. So the rotation is that Zm theta minus I equal to 0 to m minus 1 di dot alpha I. When you will rotate it, then you will get Zm equal to 0. When Zm holds 0, then theta, what is that theta? It will be your, what is the theta? Theta equal to, if Zm equal to 0, theta equal to this term, right? You will get it. In order to drive Zm to 0, minus residue angle to the 0, and di of sin is used, and your rotation will get it like this. As I told, eta whether it is a your circular codic or linear codic or hyperbolic codic, same things will be used. And zi you have to make it is 0, and because you have to make it is a residue angle 0, right? So now the residue, what is the residue angle? Initially residue angle is nothing but your target angle theta. Theta you have to make it to the 0. So that you have to make it 0, so that you will get your xm and ym, and when the zm becomes the 0. This xm ym is nothing but your k dot c x cos theta and y sin theta. Kc is your y cos theta and x cos theta. See here, I think you are well known to this rotation. I have already introduced these two part. But what is the Kc? Kc is nothing but scale factor compensation, or scale factor. This is scale factor. You have to compensate it, right? What is the scale factor? See, okay, I will come to the what is the Kc here, and then come to the vectoring mode. What is the vector mode operations? In the vector mode operations, x is given, y is a given, like vector is given. You have to compute the magnitude of your vector and the angle of your vector. Magnitude of your vector, coordinates are given, and you have to compute your uh, 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 that is called what? Length of your vector and your angle of your vector, that you have to compute it. On that case, the mode that operation, the vector mode operation, that ym you have to make it is a 0. Ym, that y-axis, the vector you have to bring to the x-axis, making y equal to 0. Okay, making y equal to 0. On that case, when ym equal to 0, then you will get the equations like the same rotations you have to look at, that xm, after the final rotations, you will get kc equal to square root of x square plus y square. This is a full square. Okay, up to this is full length of the square, not only x square. This is square root of x square plus y square. Okay, and ym you are forcing the 0. And what is the angle it will when you are bringing the vector y to the 0? I means you are bringing the vector to the x, means you are rotating, you are bringing means you are rotating with some known angles that coming to the it will align with your x-axis. So how many rotation, micro rotation you will rotate it, that addition and subtraction will you do with respect to your x-axis, then that accumulated angles will be your zm, and zm is your theta plus tan inverse y by x. Theta plus tan inverse y by x. That what you will get your final angle to be as a resultant, you will make it. Okay, you will get it. So that I means if theta equal to 0, then you can get that rotations. Then what is the angle you will get it? That tan inverse y by x. That vector rotations you will get it. The original, what is the rotated angle, that you will get it. Assume that theta equal to 0, and vector which is that is your alpha, you will get that tan inverse y by x, obviously. Okay, so you will get it, so that you can calculate the final rotation angle, the final angle, or the angle of your vector you can calculate here, and magnitude of your vector you will calculate at the xm, final xm value. Okay, final xm value will give the magnitude of your vector, and the final z values will give you the angle of your vector. So this way, rotation mode and vectoring mode, you can take care of it. So what is a Kc? As I told that it is a scale factor. This is scale factor. If you look at the cos alpha 0, cos alpha 1, cos alpha minus 1, there is a term, product term, product term of your cos alpha I. This will, when I will derive the next equations, I have neglected, I have ignored this equation, this term. Okay. Finally, if you ignore it, then this equations, what is the resultant will relate it, it will go to the magnified form. It will be magnified times x 1.674 something, it will get magnified. So to compensate it, you have to either you have to use a one divider, right, or you can use a multiplication of inverse of this amplification factor, and or you can use the some different techniques. So this is the scale factor. So that is what I have written here, the scale factor compensation, how to do it. Now this is the rotating and vectoring mode I have introduced to you. As I told that very quickly I will go that eta equal to, first is a circular mode, rotating and vectoring mode, and what are the trigonometric and hyperbolic or transcendental functions, and you will get it out of this. So if you look at the eta equal 1, then if you are circular mode, circular CORDIC, then rotation vectoring mode, you can get your this x cos theta and y sin theta. So for example, if you look at x and y equal to 0, say x equal to 1 and y equal to 0, what is the resultant you will get it? You will get your kxm kc cos theta. So kc, suppose it is concentrated, so xm you will get your cos theta, and ym you will get your sin theta. Assume that initial vector x and y equal to 1 and 0. Then xm is your cos theta, ym equal to sin theta, right? So assume that Kc is a compensated. Similarly, vector mode, you will get this one xc x square plus y square. You can calculate it. And if you come to the linear mode, you will get that if x equal to say it is a linear mode. Yeah, in a linear mode, you will get one term that is your rotation mode x and z, and x and z, right? So if you want to make it, so if you want to get your z value equal to 0, say then you can multiply with your x and z values. Assume that y equal to 0, some value x and y equal to 0, and z is having some value. Then you will get the, as a resultant ym equal to x into z. Similarly, you will get in the, if you rotate vector z, then division of y and x, you will get it here. Okay, in the vectoring mode of your linear CORDIC. So similarly, for the hyperbolic CORDIC, you will get it cos hyperbolic theta sin y hyperbolic theta. Assume that x and y equal to 1 and 0. Similarly, vectoring mode also, you will get x square minus y square term. Unlike your x square plus y square in circular CORDIC, here you will get x square minus y square term, and here you will get your 10 hyperbolic inverse y by x. So using this standard equations, by putting your initial values, you will get your corresponding cos theta, sin theta, multiplication, division, and hyperbolic cos hyperbolic, sin hyperbolic, and etc. Right. Out of this, also you can compute your exponential functions. Exponential EFW is nothing but your sin. You can represent sin hyperbolic W plus cos hyperbolic W. So once you will get your sin hyperbolic W and cos hyperbolic W from you using your hyperbolic CORDIC in rotation mode, then you add resultant, you will get your exponential value of your W, provided W is your, you have given the theta, that W value you have given as an angle to your hyperbolic CORDIC, which is operating in the rotating mode, right? You will get your exponential. So similarly, ln functions and square root functions. So for the ln functions, what it has to be rotate in the this is a 10 hyperbolic y by x, means that you have to rotate in the vectoring mode, hyperbolic in the vectoring mode, and where you have to put x equal to w plus 1 and y equal to w minus 1, then you will get the ln of your x w value, ln logarithm value of your w, right? And similarly, if you want to calculate the square root, then you can rotate your hyperbolic CORDIC in a rotation mode, vectoring mode, assuming that x equal to w plus 0.25 and y equal to w minus 0.25, so that you can get square root of your x square minus y square. Okay, so if you give this one, if you just modify it, you will get this way. So this is simply arithmetic equations to be solved in 1 or 2 steps. You will get directly it. Assume that w equal to 0.25 and y equal to w minus 2.25. So you will put it, then that will be your square w, square root of your w, right? So you will get it. So these functions you can get from your CORDIC. So see, as you understand, if you look at these algorithms, this is nothing but your simply addition and subtraction is required. There is no need of the multiplications. So simply addition and subtractions you can do. You can compute all your linear, trigonometric, and transcendental functions. You can compute it. Many computations, many such functions you can compute by simply adder subtractor. Okay. So now you come to the architectural part. So if you come to single stage architecture, you will you will get it this mapping. If you come to the architectural mapping of your CORDIC algorithms, so these 3 equations, if you look at xi plus 1, yi plus 1, what is happening, that xi plus 1, you will get it addition of xi, assume that eta equal to 1, then di will come somewhere. Then what is happening, yi to the minus I, yi was the xi and there is a operation yi, shifted version of your yi. Okay, shifted version of your yi will get either addition or subtraction depending upon your di. Okay, and similarly for the yi plus 1 you will get yi and shifted version of your xi, shifted version of your xi will get addition or subtraction depending upon your di. And how you are calculating di? Di can calculated okay, so similarly zi plus 1 you can have a zi minus di of alpha I. This equation we have got it. So di you are computing from your sine of your zi, residue angle. So sine of zi means that you can check your MSB. MSB represent your sine of your that value, that magnitude, and that d zi, take the zi MSB of your zi. Okay, and that di will go for here, and that will decide. So one path will be subtractor, then another will be adder. If it is adding, and this will be a subtracting. So it will act a adder, then it will become subtractor. Then if it is a subtractor, it will be a adder. So like that it will happen, because this is one a minus operation, another a plus operations. Okay, so if it is a plus, this term will get subtracted, this term will get a additions. So that can be decided with your di. Okay, and as I told that and alpha I, alpha is 10 inverse 2 to the minus I. This alpha I 10 inverse 2 to the minus I, this will be stored in a small lookup table. Small lookup table depending upon the number of iterations. Suppose your bit size is 16, then you need a 16 iterations. So 6 iterations means 16 micro rotation angles, that is known angles. That 16 micro rotation angles you have to store in a one lookup table, small lookup table of size 16. Okay, that you have to store it, and every time you have to retrieve one after one, going for the addition and the subtractions in this path. Okay, so this is single stage, but if you go for the rotation, okay, this is for the hyperbolic. Okay, hyperbolic means that here only the sign bit you look at it equal -1. -1 means this is effectively it is a plus, this is plus. So both will be get additions. Okay, here both will be act like a adder, both will be act like a subtractor depending upon your di value. And you have to, what is the differences? 10 hyperbolic, that lookup table you have to change it, but otherwise the step is the same, right? Similarly for the linear CORDIC, if eta equal to 0 means this total term is a 0. So xi plus 1 becomes your xi, and yi plus 1 becomes the shifted version of your yi. So xi will get adder or subtractor from your yi. So yi, and it will get it will be the shifted version of your xi will get adder or addition or subtraction from your bit or from your yi, right? So you will get your yi plus 1. Of course di is a residue angle of zi, and what is your lookup table? 2 to the minus 1, 2 to the power minus 1. So this is the changes you have to do when you will operate in as a linear CORDIC. Okay, so I think this up to this stage all of you are clear, but the single stage and in ith iteration and what is your basic architecture. So if you go with the iterations to compute the final values, then there are different architectures to will get it. One is called a folding or recursive architectures, or unfolded architectures, and unfolded with pipeline architectures. So depending upon your performance, speed and area performance, you have to choose either of these three architectures. So if you go to the iterative architectures, so what I have done here, nothing but I have done, see, this is single stage till this point I have we have done it. What I have do, like the output of the first stage, present stage will go to the next stage for the further stage computation, next stage computations, right? So it will keep on iterating for the m cycles. At the after the m cycles, you will get your final values. Xm equal to x naught cos theta minus y naught sin theta, ym equal to x naught sin theta plus y naught cos theta. Okay, now everything is same, and this rotation I can control with a one block, that is a counter. This counter will decide how many iterations you have to want to rotate. Okay, so if it is a 16 iterations, so I need a 4-bit counter. So 4-bit counter will keep on rotating these vectors, and finally once it's computed after the 16th cycle, you will get a final output from this demux as a xm equal to x naught cos theta minus y naught sin theta. You will get it. And obviously and y equal to x naught sin theta, y naught cos theta. And if I rotating for the rotation mode, zm becomes the 0, right? And if you look at, if x naught equal to 1 and y naught equal to 0, then xm becomes your cos theta. Final, what is the value will get at final rotation? It will be your cos theta value. And in this y variable, what is the final value will get it? That is your sin theta, isn't it? So this is the rotation architecture, you will get it. If you compute the throughput, see, whenever you talk about the architecture, there are mainly two performance parameters we consider, that is throughput and the latency. What is the throughput? Throughput is nothing but number of outputs per second. Number of outputs per second, right? That is called a throughput performance. What is the latency? How many cycles, how much time it will take, to get your first valid output or output. Okay, that is called your latency. This is the if you talk computer performance, the any architecture that should be high throughput and low latency. It should take minimum cycles, minimum time to give the output. So if you talk about high performance computing, then any architecture, the characteristics of the architecture is that it should be high throughput, low latency. Okay, so if you look at this architecture, what is your throughput? I'm talking about the qualitative parameters. So if you look at the first stage, what is your critical path? Critical path is nothing but your shifter and adder and subtractor, right? So in each stage, it will take the time of your shifter, time of your adder and subtractor, right? So the cycle, the CORDIC has to be rotate. It works with a clock frequency which is having the time period of t adder subtractor plus t shifter, and to give the output after the m iterations, it requires the m cycles. Now, so overall cycle, it will take the m cycles. So what is the time it will take? M times t add subtractor plus t shifter. This is what? This is much time it will take it. So in this time, m after m cycle or m times of your t add subtractor plus t shifter, you will get one output. So in 1 second, that's the reverse, right? 1 upon this. So that is your throughput. So throughput is nothing but 1 upon m dot t add a subtractor plus t shifter. That is your throughput. So depending upon your delay of your adder subtractor and t shifter, you can measure your throughput depending upon the m also. How many iterations you are taking, depending upon your bit precision of your x naught and y naught. Okay, or that is your z also. Input operands. And the latency, as I told, that it will take the m cycles to give your outputs. So this is the latency it will take. So this is the drawback of the CORDIC, that it will take the m cycle. So latency is a high in CORDIC algorithms. This is the limitations of the CORDIC. So this can be overcome. Another alternative architecture, that unfolding architectures, like if you the all stages you will connected together, you will get it. It will compute in a single cycle, but the cycle of your cycle of your clock cycle of your time period of your clock cycle becomes your mt add subtractor, m times your t adder and subtractor, because this stage 1, stage 2, stage 3, if you go like this, then every stage how many bits it will move. In the first iteration 1 bit, second iteration 2 bits, third iteration, third bit. So this is a known bit to be shifted right. Okay, so this right bit, known shifting, known right bit shifting, you can do with a hard shifter. So you don't require any dedicated shifter to implement on it. Okay, so only the critical path remains your adder and a subtractor, adder and a subtractor. So the throughput becomes your 1 upon m d add and subtractor. If I go with the pipelining means I am introducing the register in each stage. I am introducing a register in each stage. So I am introducing the register in each stage. Means that first sample will operate at the stage 1. The output of the first sample will go to the second stage, and the second data will be get executed in the first stage, and the output of the second stage will go to the third stage, output of the first stage will go to the second stage, and new data sample will come to the first stage. So it in pipeline version, it will go on up to the m stage. After the m stage, you will get a first valid data, and after each cycle you will get the every cycle, in every cycle after m cycle, I mean like after m stage, every cycle you will get, you know, valid data for each sample, input samples, right? So the throughput, what is your throughput now here? The throughput is your 1 upon T8 subtractor, because the time period of your clock is your T8 or sub. Since every cycle it will give in a one valid output, then throughput becomes your 1 upon T8 or subtractor, right? But here initial latency will be there, that is a m cycle. But till m cycle you will not get any valid output. So initial latency will be the m cycle, it will consume the m cycle, but after m cycle, each cycle you will get your one output, and that is your, that will give you a throughput performance, very high throughput performance. So generally, you know, pipeline architectures give the very high throughput. So it proves that you will, you know, if you look at the throughput performance of your iterative architecture and the throughput performance of your TID, m times it is increased, it enhances the m times, right? M times it is increased in the pipeline CORDIC architectures. So generally, to though it is but obviously the what is the drawback of the pipeline architecture? Because here you need only one stage of the you know, adder and shifter in iteratively are using. So hardware is less in the iterative CORDIC, but pipeline each stage you are repeating. So m times hardware you are using in your pipeline architecture. So it is again, it is a performance versus your hardware. If you increase your hardware, your throughput performance will be increase in your pipeline architecture. Your throughput performance is increasing, but you know, hardware is increasing. So this is your, you know, pipeline architectures. So what is a scale factor? What is the limitation of the CORDIC architecture? I told that one is a scale factor and another is a computation limit. Computation limit minus pi by 2 to the pi by 2. As I told that it compute only first quadrant to the first quadrant and fourth quadrant, and obviously the computer latence, what we have discussed. All three things we have discussed, but I will address how to sort it out. So this scale factor, as I told that this scale factor for the circular CORDIC it is a 1.64676. For the linear CORDIC it is a 0, and for the, you know, hyperbolic CORDIC it is a 0.828159. Okay, so this is a if it will go with typically some iterations, so you will get these values from your known equations. So so these factors has to be compensated, right? This factor has to be compensated. So so hardware activity is derived by neglecting scale factor k, but it has to be compensated by a factor 1 upon k. Okay, this is your amplification factor. Then scale factor compensation you have to do by 1 upon by k. So scale factor and compensation can be done using two parallel CORDIC. Either you have to use the multiplier or a divider, or also using the CORDIC also you can compensate it. Okay, so how to do it? That is called a parallel scale compensator technique. Rather than single CORDIC, we can use the two CORDICs in parallel, where phi you can compute phi another angle, that is a known angle. Phi can be taken as a cos inverse 1 upon 2 kc. Kc is a known value, so phi is a known value. So your target angle plus your this known value can do it and rotate. One is a positive side, another is a negative side. When one CORDIC you add it, another for another CORDIC you subtract it. If you do it, then you will get your these equations. You will get these your equations. See, one is addition, another is subtractions. If you add addition, what is the resultant? You will get it. Finally, xm and xm plus x minus 1 will give the xm cos inverse minus 1, ym plus y minus 1, it will give the ym into cos inverse 1. So if you put it here final rotation angle kc inverse, what you will got it from here, you will get the final rotation angle which you will get compensated automatically because of this factor kc inverse 1. So initially it was kc, this term you will get kc inverse 1. So that kc inverse 1, kc will be compensated and you will get finally your xm and ym from your addition of your two CORDIC rotations. xm x I plus 1 this side, sorry, and y plus 1 this side, similar for the ym. Okay, so this way you can compensate parallelly without adding the initial latencies, any latencies. Okay, otherwise you use a CORDIC, another vector CORDIC also used in the series for the multiplication or division, you can compensate it. So two CORDIC has to be implemented in series so that you have to compromise with your latency. But having the same latency but same hardware, you can get your scale can be compensated. Computation limit, how to extend your range. So this is, I can compute in the first quadrant and fourth quadrant. I cannot compute in third and fourth quadrant, right? So what it does here, that 0, 0, you compute it. What if any angle lies in the second quadrant and the third quadrant? Take this quadrant to the this side and this side, okay, and compute it in the first quadrant and fourth quadrant, and get back to here by transforming your x-axis. Suppose x is there, put the negation 2's complement, it will come to this axis. If it is there this axis, y is a minus 1, so this axis, then take the 2's complement to 1, it will go to the middle for the four, get it. Okay, so this way, so this can be done by assuming the angle that minus pi by 2 vectors, that I will use the angle weightage, I will give it minus pi, pi by 2, pi by 4, pi by 8, like that. So last 2 bit MSB will decide by where the quadrant. So 0, 0 means it is a first quadrant, 0, 1 means second quadrant, 1, 0 means third quadrant, 1, 1 is a fourth quadrant. So these 2 bits will decide which quadrant it is. So accordingly, if it lies in the second and third quadrant, what I do, that I will take the second quadrant to the fourth quadrant, right? Second quadrant to the fourth quadrant. What I do, this MSB, you will like copy to the this MSB, then second quadrant will go to the my fourth quadrant. If third quadrant 0, 1, if I copy this 0 to this bit, means 0, 0. Remaining bits are remain same. So then it will go to the first quadrant. So I can now compute it and I will return back my final vectors. So that way you can extend your angle and you can extend your computation of CORDIC to the all 4 quadrants. So this is the way you can do it. And another is a computational latency. Very quickly I will go. As I told, this is the computational latency. There are many methods, like adder subtractor is a main bottleneck. So you can go with the faster adder and subtractor, like carry save adder, Hank-Carlson adder, sign digit adder, so that latency can be minimized, throughput will be increased. And another way that fast algorithm, CORDIC algorithms, there are many algorithms, radix 4 algorithms and double step CORDIC algorithms are there. But we have proposed that is called a low latency hybrid CORDIC algorithm and architectures out of this. But what we have hybridized these 2 algorithms and proposed a new algorithms that is called a low latency hybrid CORDIC algorithms. So if you look at the radix 4 takes the n by 2 iterations for n bit precisions. So these are the computations you have to do it. And the double step will take the number of iterations n by 2 for n bit precisions. So these are the equations for the double step CORDIC algorithms. These steps you have to compute it. Double step CORDIC algorithms architecture bit different from your additional hardware to have to introduce compared to your IT to CORDIC. Normal Redis to CORDIC. But here the scale factor is also a big issue. On Redis 4, the scale factor is a big issue. It is not a known because it has to rotate many plus or minus 2. Sigma is a plus or minus 2 plus or minus 1 0. So it is not a constant. So like Redis 2 CORDIC. But in the double step, it is similar to the Redis 2. So it is can be done with the same multiplication factor, scale factor compensations techniques. But we have what we did it. We combined these two algorithms. We got these algorithms for the hybrid CORDIC algorithms. This is our algorithms. We have combined both, including your scale factor, because here scale factor is also not known. It is a variable, so we have to compute it. Again, here we have used the approximate, Taylor series approximate arithmetic, because this computations you have to do with approximate it Taylor series. So we have taken this one Taylor series up to the first 3 terms we have taken. Okay, up to the first 3 terms we have approximated. We have calculated our scale factor, and that rotations we have done it, and each stage we are compensating our scale factor also. So this is for the scale factor compensations. So this is the rotation angle including my scale factor. So this is the final first order architecture for the low latency hybrid CORDIC. Why it is called a low latency? Because number of iteration it takes 3n by 8 plus 1 for n bit precisions. This is the latest architecture as of now. Nobody has proposed till now. Nobody has challenge to our this architecture till now, and which is giving the iteration is a 3n by 8 plus 1 is much less than your normal CORDIC. You can get from your architectures. So we have compared with, you see, this is our architecture, hybrid low latency hybrid CORDIC architecture. If you look at the bit precision, see, if you bit precision is high, you see that our iteration number of iteration is very less compared to the other state of art architectures. Till now, nobody has challenged to this iteration performance and throughput performance of our architectures. Of course, we are giving some hardware compared to them, but iteration is much less compared to the other architectures. So still there is a chance, because the latency is a big issue in the CORDIC. So still there open problem to minimize the number of iterations. Okay, so this is all about CORDIC algorithm and architectures. I have talked about. I think it is almost 8:38. Yes, time is there. We can compute. So then you will go to the unified windowing architectures. That we go to the how you deploy this CORDIC algorithm to get our windowing architectures or windowing function to compute the windowing functions. So look, I have already told that we'll do the time domain windowing. I have already discussed. So what is happening? This is the sequence you will get it. If you do the windowing, if you rectangular window, if you look at, so you will get this much same signals you will get it. But you will go to the specialized windowing functions that outputs will be smooth. At the end, it will directly be not truncated. It will be smooth, so that you can minimize your spectral leakage. So this is what time domain multiplications you have to do. So we will implement these equations, these right side equations in a windowing functions. So what is a WX windowing functions? The various windowing functions you will get it. What are those? So if you look at the more commonly used Hanning window, it is again Hanning window and Hamming window, Blackman window, flat top window, Kaiser window, then Black Harris window. So many windows you will get it. So one by one we will go. So simply Hanning window, if you look at the Hanning window, simply Hanning window, then Hanning window is 0.5 plus 0.5 cos 2 pi n by n, right? If you multiply with x, so x has to be multiplied with 0.5, means this hard shifter, and yin has to be multiplied with this 0.5 cos 2 pi n by n. So this cos 2 pi by n you can get through the CORDIC, and which has to be operated with a vector x, right? So this what you xi will get it, that has to be passed through the FIFO for this addition operation till this circular CORDIC you can implement, you can get completed. The computation on the circular CORDIC can be completed. So theta you can give theta n, that is your theta n you can give depending upon your capital N, that is 2 pi n by n. So angle generator architecture you have to use it, and you have to give the theta n to the circular CORDIC, and obviously xi is coming to here, so you can get the cos theta. So cos theta you will get from your x-axis, right? Cos theta you will get from your x-axis of your CORDIC rotation. So xm value you will take here, that is final resultant xm you will get it here, and though that xm which is shifting, multiply with 0.5, that has to be come here, right? So that you can get the addition in final value, final time domain input signal output time domain sorry output of your time domain values you will get as a S naught from your windowing functions from the Hanning window. So this is one. So you require one FIFO, one circular CORDIC, and one angle generator architecture, and your block, and one adder. So this is very simply, one Hanning window, because 0.5 is nothing but 1 by 2. 1 by 2 can do with the hard shift by 1 bit right shift. If you come to Hanning window, the coefficients are 0.54 and 0.46, right? It varies, and cos 2 pi by n. So these multiplications you have to do 0.54 and 0.46. So to do this, you have to multiply, then you have to use the linear CORDIC. So which will go to the circular CORDIC, one linear CORDIC to multiply 0.46 and another with the 0.54. You have to do it. So then you can get your FIFO, then you will get your Hanning window. If you come to a Blackman window, then this is the equations, 0.42, 0.5 cos 2 pi n by n, 0.08 cos 4 pi n by n. You can get it. And this is three terms. So you require a two CORDIC, two circular CORDIC, two linear CORDIC. Okay. Obviously, there is a FIFO you have to take care of it. And that way you can get your output here. And obviously angle generator you have to do, which will go to the circular CORDIC of these two part. These two, when these two terms to compute these two terms, right? So this is about your black window architectures. So here that one is a angle generator, right? Angle generator architecture. And if you look at the angle generator architecture, there is a, what is that? Theta n plus 1, I can break this 2 pi n by n or 4 pi n by n. So talk about 2 pi n by n. So you can easily calculate 4 pi by n multiplied by 2 means shifting one bit left. So you can compute this angle 4 pi n by n. So n is varies from the 0 to n minus 1, you can say. So if you theta n plus 1 equal to theta n plus 2 pi by n, that known angle 2 pi by n, theta I can vary, theta n I can vary, right? It will vary. So I can use the C, and the encoder part, you get your n, and loadable down counter. I believe this is the architecture I can put it, and 2 pi by n, it will be shifted by log n bit to the right shift. I will do it, and I will get register, means I will get here 2 pi by n. This 2 pi by n will get always added with your incremental angle, incremental angle. So initially it is a minus pi, and then what is the value it will get it will get added with this one. So it will show on, it will keep on, okay, adding, so that you can generate your this value theta n plus 1, which will go to your circular CORDIC, these two circular CORDIC. Obviously the theta n, another phi n is a twice of your theta n. So this is a shifted version of your phi n, you can take it hard shift, that is a left shift you have to do, so that you can get your phi n. So theta n go to the one CORDIC and phi n will go to the another CORDIC, you will get it. Another is a block, which one you will get it is a shifter, right? In the CORDIC, you require a variable shifter if you are implementing, or even if yeah, loadable down counter encoder, shifter blocks, it is known. Okay, yeah, this is shifter. So depending upon the value, that log of n, how many angles you have to generate it. So how many angles you have to generate it. So this what is written here S30, actually it is a 3C3 colon 0 3C. This is S nahi, S, it is not S, it is a C. The C is coming here. This is shifter. This is a variable shifter. So this variable shifter I can use the 8-bit conditional right shifter, 4-bit conditional right shifter, 2-bit right shifter, 1-bit right shifter. So I will use 1, 2, 4, 8 so that I can have a 16-bit. So if it is a shifted by 8, it is shifted by, but like it is hard shifter. So it will, this block, it will hard shifter like one, not hard shifter, it will shift by 1 bit. Okay, so this 1-bit conditional shifter is that if you want to shift 1, say suppose it is 0, 0, 0, 1. So 1 means that it will shift. See, look at S10, S11. So this is the input side, right? If we know, if S equal 0, S of C of 0 equal 0, then this the same value will come. If it is a 1, the shifted version will come. So S1 will come here, S2 will come here, S3 will come here, C for input will come here, input. So these are our input, not the S. These are input values. Inputs will come here as a output. Okay, the index I have done mistakes here in the drawing. So these are input will be shifted by 1 bit. Okay, so depending on the mux, which one you are giving 0 or 1. If it is 0, same values will shift here. If it is 1, the bits will shift to 1 bit right. Similarly for the 2-bit, like this you design for the 2-bit, means that instead of here to here, you have to take this bit to here, this bit to here, this 2 gap between two gap, 2 data sample gap, you have to take it. Okay, so this one you can get 2-bit, similar 4-bit, 8-bit. So the selection of this, if you give 0, 0, 0, 1, then 1 bit shift. All are 0, 0, 0, 0, 0, then no shift, input will come as output. If it is 0, 1, 0, 0, 1, 0, then 2-bit, because there is no shift, here 2-bit shift, here no shift. So 2-bit shift, get it. So if we all are 1, 1, 1, means here shift 8-bit, here shift 4-bit, here shift 2-bit, here shift the 1-bit. So we will total 16-bit, it will get shifted at the resultant. So this is which one, this is my architecture. So I have proposed this architectures for this variable shifter. This is the variable shifter, you can implement it. So see, if you look at the performance analysis, ROM based, the classical implementation is ROM based, and another our approach is a CORDIC-based. So if you look at very qualitatively, critical delay is your T access, memory access time plus T multiplier. And in a CORDIC-based, as I told, that if you go with the pipeline, then T adder plus subtractor. And the flexibility, there is no flexibility. You cannot change your n. Once n is decided, ROM will be decided. You cannot get the different coefficients. But if you go to the CORDIC-based, then you can change the n. You can get the, based on you will get your coefficient that depends upon your angle generator architectures. That will can generate from the angle architecture and CORDIC, right? So that coefficient can be generated. Okay, so you means that you can have a variable windowing length, and sometimes it is very, very useful for the short-term Fourier transforms when the window is getting varied. Okay, so that depends on why you are STFT. If you go to window varying of the window, that depends upon your bandwidth and your that is called resolutions. So then if you go to the implementation performance parameters, humming, and black main windows, we have synthesized, implemented on the Verilog HDL, and implemented, synthesized using the 180 nanometer technology, CMOS technology, and implemented both adder and slow adder, like replicator adder and one fast adder that is called Han-Carlson adder. We have experimented, so these are the performances we will get it. So if you use the Han-Carlson adder, the maximum operating frequency of the CORDIC is coming 400 megahertz. Okay, and throughput is a 400 megasamples per second. Obviously, latency is a 34. Okay, so this one for the Blackman and Hamming and Hamming window, because this no critical relay is a T adder subtractor, so that's why it is coming this performance we are getting. Now what is happening? The constraint that either you do the Hamming window, or Blackman window, right? So once one application is ready, you are going for the application specific. So one window you can employ, you can design and employ it. But if once you design an ASIC, application specific integrated circuit, you cannot change your window functions, right? So it is only work for a particular window which one you have implemented. So to have a flexibility, we have given a architecture that is called a CORDIC-based unified windowing architecture. What it does, so it can compute the Hamming window, Blackman window, depending upon your choice. So this is the generalized equations. The new alpha, beta, gamma coefficients for the Hamming window, Blackman we have pre-decided, and that will go to the CORDIC for the comparisons. So this is the architectures. What we have done it, we have taken the maximum hardware, and the coefficients A, B, C, D, E, F, G, that coefficient which we are getting from your this alpha, beta, gamma, we have decided, and this coefficients we have selected, and input we are giving to the each CORDIC, and you will get your output like this. So these functions we have implemented, and to implement these architectures, or this architecture is designed to implement these functions, unified functions. Here the window selection you can do, whether Hamming or Blackman, you can do it. Okay, and also see sometimes if you go to Hamming window, maybe for the Blackman all blocks can be executed, but Hamming window all blocks will not needed. So for that, some of the blocks you can put into the power down mode. So power down circuit we have given with this very simple logic, and which will give you the put some of the blocks to the power down mode, so that you can consume the less power. It will consume the less power from the source. So but you see though it adds some few hardware, but the flexibility that you can select your window depending upon your applications. Once you design your application specific, once you have fabricated your circuit. So here the maximum operating frequency, the performance is that operating frequency 125 megahertz, because we have implemented this one using replicator adder, and maximum core area it is 11 mm square, and it was consumed the power is around 350 milliwatt. Okay, so at this frequency it was taking the 350 milliwatt. So this is about CORDIC-based unified windowing architecture. Further, what we did it, we have incorporated another architecture, that is a flat window and top flat window and black Harris window, to Hamming and Blackman window. Then out of this we got our unified architectures with the all coefficients you got it, resultant coefficients, final coefficient you got it, and incorporated to get your outputs. So let's really come to the what is the input signal look like. So this is the I'm repeating once again, this is a rectangular window. You will get this type of signals as a output that will go to the Fourier transform for a rectangular window, and this is the zoom version, and this is for the different black top flat black Harris, Hamming window. All this is for the rectangular window, and all 6 windows it will come off like the output of your windowing process, which will go to the FFT as an input. So depending upon the smoothness, you will get your outputs. So these 3 windows will give the very good output compared to these 3 windows. Okay. This is the frequency domain signals. You will get it. We have shown it. And if you look at the you have how to choose your windowing parameters or windowing functions depending upon this main lobe width -3 dB, 6 dB main lobe width, highest side lobe level, side lobe fall off rate. So depending upon these parameters you require for your applications, you have to choose the particular window. Okay, so window selection you have to do it and get your windowing output that will go to the FFT. So this is the final architectures of your popular window where you can compute all 6 window functions. So this is the design. This is the design. This is the final architectures. See the angle generator architecture, which one we have here, the angle generator architecture, and it is a very another shifter we have very, we have taken. This is the angle generator architecture we have given, but this shifter we have handled bit differently. Assume that there is a 2 pi angle is present. So very simply hard shifter. Depending upon your n, you can get your the resultant values. So we have not used the variable shifter. We have used the hardware shifter by arranging only the shifting arrangements. So it is very clear. Like if you look at the n equal to say 8, 16. So 1 0 0 0 0 it will come up. So if you divide by n 16, so what 16? So this MSB will come to the here. Okay, so all becomes the 0 0 0 0. This becomes the 0. So it becomes your 2 pi by n. So that way you can by define hard shift you will get it. The depend the n value, n will be a variable also, but this simply shifting operations you can get your that operation 2 pi by n. That 2 pi by n you can get it. So that is this method is better than the variable shifter initial what I have had proposed. So this is all about architecture, and we are not there. We have done the ASIC implementations, and also we have a prototype on the FPGA. So this is our experimental setup. In laboratory experimental setup, we have implemented on FPGA. We have taken the low end FPGA only. That is a Spartan 3 FPGA board. And we have done the taken the input signal from the function generator. We have given all the windowing function. We have generator windowing functions, and we have got your output also, spectrum also from the spectrum analyzer, using the spectrum analyzer of your spectrum analyzer. So that function using your FFT function using your spectrum analyzer. So this is the output laboratory experiment setup. We have done it. So these are the outputs. This is our MATLAB simulation output, and this is our FPGA output for the windowing functions. This is for the we have taken. This is for the flat top window, and this is for the Blackman Harris window. It is very close output we are getting. Of course, there should be some error because you are going to MATLAB is working on the floating point, and in your hardware works on the fixed point. So obviously there will be error. So this is a Blackman window. I'm very quickly I'm going, and this is for our Hamming window, and this is for the Hamming window. Almost we are getting the same output, and this is for the spectrum input signal and the spectrum of the input signal. Spectrum we have calculated from your without using any window. We have got it, and once we have implemented the window, then we have got it. These are the performance. See the green color, the without window. Using the flat top window, we got this performance, spectrum performance, right? And this the is just many side lobe. These things are getting reduced, right? It is getting reduced. This is with the Blackman Harris window. This is with the Blackman window. This is with the Hamming window. This is with the. So if you look at the performance what you will got out of the FPGA prototype. If you look at this is the performance we got it. Our proposed window. We have taken our proposed window, taken to your FFT of your spectrum analyzer, and we have given directly the our signal using the window of the FFT. See, if you go to the spectrum analyzer, it will ask you the which window you will select it. Rectangular window, Hanning window, Blackman window, like that, right? So what we have done it, we have used the FFT window with our proposed window. Also, we have used the FFT window of the spectrum analyzer. So what is they have implemented through the ROM-based implementations. Then they implement the spectrum analyzer. They have implemented through the ROM-based implementations, memory-based implementations. They have done it. So we have compared with the these are the output in terms of main low power, and another also occupied bandwidth. It is very close. Obviously, there will be a deviation, no doubt at all, but we have got it. And these are the performances we got it, and maximum side lobe also we got it. If you look at this is 53, this is 63. So side lobe window we are getting very less. In we are getting advantage in our window compared to the our flat top window. That is with your spectrum analyzers. So these are the performances. I'm not going to the detail. We have compared the inbuilt window functions of your spectrum analyzer and our windowing functions taken from the FPGA. So these are the errors. We have calculated analytical absolute errors, and this is the experimental absolute errors. We have computed red color is absolute error. So error deviations we are getting from for the each windows. This is for flat top window. This is for the Blackman Harris window, and Blackman window, Hamming window, Hanning window, like that. Okay. So these are the obviously error will be there compared to the your MATLAB or an analytical computations because of this fixed point, and also this approximate to what we have taken, approximation we have taken, that will lead to your errors, right? Error is there, but it is a tolerable. It is a tolerable. So now windowing function is done. Then come to the running DFT architecture. I will take another 20 minutes to complete it. I don't know. Time is 9:02. I will take 10-20 minutes, and after that we will go for the discussion. Let me complete it. So come to the running DFT architectures. What is the running DFT? If you look at what is its advantage, that we'll look at, and after that we will go for the computations. Real-time spectrum analyzers, as we discussed, generally employ the FFT, right, along with a ping-pong buffer technique. Ping-pong means that it will take the block of data, compute the output, then next it will take next block of data, compute it, next block of data. So it is a ping pong buffering. It will take first set to the buffer, then next set to the buffer, next set to the buffer, and keep on processing, right? That's why it is called a ping pong buffer technique. So data will be put to the buffer as a block, in a block. So then what is the constraints? Design constraints. Design constraint in such cases should be that FFT computation must be completed by the time the next block of data, whose size typically equals the length of the transform, is gathered in a buffer. So before the data come to the buffer, your FFT computation to be computed by the time. Then it will take the next data and compute it. If not, then it overlapping will happen. You will get the next wrong spectrums, wrong outputs from your spectrum analyzer. So that is one problem you will get it. So such block-based schemes are having at least two drawbacks. One I already told, that output can be updated only once in a block period. Only once in a block period. And another is that short library periodic signals, partial spanning over two successive blocks, are not being captured properly. You are taking first block, second block. But short living periods, which is short life means that one valid signal which is a short life, which comes a short duration, and which come between the two blocks, what you are taking. So then you are losing the maximum number of informations of that short lived periodic signals. And this is a very, very bottleneck on the biomedical signal processing, if you look at ECG or EEG, where each sample or each short period of the sample, it will essential, it is a valued, and it is a contains the most information of your health that will miss while going for the FFT computations. And as I told, short life, suppose you are doing firing will for short duration one signal will come, other is a zero, but signal will come at a very for short duration if you are doing the firing means gunshot. So if you go to the ping pong, you may miss that short duration signal, or you may miss partially short duration signals, that gunshot signal. So this is the issues you will get it. So you cannot get the correct output, correct analysis when go to the this ping pong based techniques. So to overcome this problem, the another method for the computation of the spectrum is employed, that is called a sliding window, and conventionally it is called a moving window. Okay, so we are using the moving window with your FFT, along with your FFT, so that you cannot lose the informations of this single signal or single sample or short duration samples. So, but what is happening in this case, that it is having the problem that but this sliding window and windowing FFT architectures computations, it will have its own architectural drawback. It is suffers from the accumulation of or round off or truncation error that renders the computation useless after the finite time, because these sliding windows will operate on the iterate, similar to the IR filter. This is similar to the IR filter. Output you have to take to the input. There is a feedback. So after some time, the error will be accumulated, so that it becomes the useless the data, and you will lose the informations. Again, this is having the drawback. Once error grows beyond the acceptable limit, the buffer is required to be flushed, making the output unavailable till the buffer is filled up again. So there is again, when it grows, the error grows, your data will grow, bit size will grow, right? Then you have to flush periodically to compute fresh. So that what we have to take care of it. So this becomes the major bottleneck for deploying this running window, moving window, or sliding window in a real-time spectral analysis. See, one way it is advantage, it give you the information of each and every signal. Other side, it will lead to a error. So this is the drawback what we are getting from here. So from here, what you do, like of course this is my work. I have proposed new alternative architecture how will overcome this error. So come to the running DFT. Running DFT here means that I'm sliding the window with a one sample. You can apply for the short duration particular window you can take up, but here what I have proposed, it will slide with one sample, and it will give the spectral informations of each signal. That's what. So if you look at the FRK is a spectrum of your kth harmonic of your spectrum, that is represented FRK. R is the rth instant of endpoint DFT at the rth instant of long sequence Sn, where n is the integer power of 2. So this is the equations FRK n equal to 0, S of n plus r minus n plus 1 e to the r minus j theta k by n, where theta k is a 2 pi k by n. So this is a simply DFT. Only what I know is look at S of e to the j theta k by n. It is a DFT, right? But to have taken this indexing so that I can develop my, you know, running DFT. Okay, my algorithms I can develop it. This is I'm not developed. It is already there. This moving and running DFT is there, but I have proposed my new architectures. Here, see, if you look at the right side, the r minus 1, if you look at you know rth instant, if n equal to n equal to n plus r minus n plus 1, like that, if you look at, since running Fourier spectrum is to be updated at a rate of one sample point, which is called running DFT. So DFT of succeeding samples for the kth harmonic component at r plus 1th time instant will be, what will be? So that will be your fr plus 1. If you put r instead of r plus 1, becomes your n plus r minus 2 plus 2. Okay.
Sir,
So
excuse
yes,
sir.
yes.
Sir, more 10 or 15 minutes
Ha
because
ha.
it's already 9 minutes.
I will complete it. So
Okay.
so that way you can compute it that FRK. If you look at the FRK, so I will use this FRK FR plus 1K. So I will get the current instant from the previous spectrums. That FR minus 1 is the previous spectrums. So FR minus 1 K SR. So this is the equation I will get from subtracting from one to another one. So here FR plus 1 minus FR, but I have taken rth instant, r minus 1th instant in these equations. So this is the, what is the called spectrum you can compute using these equations. Running spectrums you can compute using these equations. So if you look at the magnitude, if you want to calculate, compute the magnitude, obviously it is a square root of it is having the real and imaginary part, this real spectrum and the imaginary part of this one. So magnitude you can get square root of this one. So this magnitude you can calculate using your vectoring mode CORDIC. Once you will get your this one, every time you get your this rotation you can do with your rotational CORDIC, and this magnitude you can get your vector CORDIC. So if you look at the last equations, matrix forms, if you look at this is the last equations, you will get it where delta SR equal to SR minus n. So if you put it this one, I mean SR minus SR and minus 1 you can get by using the subtractions. Delta SR get it, delta SR, and that you can give to your CORDIC, and finally you can get your magnitude at the end using your magnitude vector CORDIC rotating on the vector mode. So this is the architectures. This is the implementation what we have done it. But what I have done it for the each component, kth component. So I have taken for the kth component. You can compute the for each component, one first component, second, third component, third component, like that. You can compute it, and you will get your kth component. All components you can get the component, like spectral components you can get it. 0th component, 1th component, kth component, and minus 1th component. Each component you will get it. And if you see that this is the window, the buffering I have doing here, SR minus 1 to the SR minus n minus 1, each cycle one sample is getting into the buffer, and you are getting the output. So initially for the one buffer, you have calculated the first using the rotation, you get your FRK and FRK. This is a real part, this is imaginary part of your spectrum. I will compute it, and after that each cycle one sample will get into the window and the last sample will go out. So what is the impact of the current sample to the window, your spectrum, that will reflect here. Okay, that will be reflected here, and its magnitude, obviously you can calculate the magnitude of your spectrums, the current spectrums, and each component you can highlight from each processing element. So this is for the kth component. Similarly, you can from the each component, and you can show the each component of your spectrum, how it will be changing with respect to the introducing the new samples to your window, or the current window, right? So each spectrum will get changed, and each spectrum component can get from the each processing element. So I mean, this is the one rotational CORDIC and one one rotational circular CORDIC in rotation mode and vectoring mode has to be replicate used for the one processing element. This is assume that this is one processing element that has to be replicate n times to get the n spectral components. So this is what CORDIC-based running DFT you can compute it. As I told, see, this is iterative, right? This is iterative. So if it iterative, no, there is a truncation error. So this due to this truncation error will be get, you know. So if you, I have taken with very one test signal I have taken for the demonstrations. These are test signal. If you pass it, I have calculated the one component here. If you look at that blue color is MATLAB output, because there is no floating point, no error. You will get a flat one window one. The peak of one component is a flat. But if you go to the CORDIC-based implementation, you see in each iteration, if the iteration goes on, the spectrum is getting reduced. The magnitude is getting reduced. It is so happen after some time it will get reduced and it will, the output will becomes the useless, right? So what it does, we have introduced to overcome these error accumulations, right? Error accumulations. We have done the refreshing mechanism. We have introduced the refreshing mechanism so that periodically it will refresh it with the tolerable error limit. That's what we have proposed our architecture. So here this is the CORDIC-based running DFT with the refreshing mechanism. What it does, there are two processing elements we are employing. What we do here, one we will put on the processing mode. In the same time, other we will make it in the flushing mode. We will flush it and recompute it. So once it is flushed, we will recompute it, and once it is computed, then we will do the vice versa. Previous one will be flushing, next one will be flush. So in alternately, one will be flush, one will be compute, one will be flush, another will be compute. Like that we have to do. Means we are computing one and another is getting flushing. So this is what we have done. There is a very simple flushing circuit we have taken here, and by employing that two processing element for one component, one spectrum component, so that for all n component it will be twice it will be developed. So this is what, if you look at the timing diagram, so if you look at refreshing period, in this cycle I am refreshing. So during refreshing, if look at swapping the signal, one time it will compute, another will be flushing. So if you look at the swap signal 1 and 0, one is a computation mode, another is a one is in a flushing mode, another will be the computation mode. So is a lower refreshing the lower one, refreshing the upper one. So when it will come swap it, it will be a lower signal, it will be flush it. Okay, for the upper module will flush here. In the other time, if you look at it is computing the Euro computations. So okay, so it will give you the values, and while it is flushing, other is computing. Okay, other is computing. So you can take the output of that one, and you can compute your magnitude of your spectrum component. So this way one, so it is implemented using your iterative sequential CORDIC, and as an alternative CORDIC, what we have given, we have implemented the pipeline CORDIC and FIFO. Okay, we have implemented the FIFO, so that you can throughput will be increased. So this is what here the similarly we have used the same mechanisms, only that we have improved the pipeline and implemented your FIFO buffering. So this is the cycle what we have done here. See, while it is flushing, the upper one, lower is flushing, upper one is computing, and vice versa, just because it is a continuous, because we have implemented pipeline. So every cycle we need a very valid output, valid outputs, right? So once it's flushing means it will be giving output, and the next one is flushing, it has to be give the output. So this pipeline CORDIC, because it is a pipeline, it is computing, each sample is getting computed. So we should not have any latency over there, so that you can have a, every time if you particular instant of time, one CORDIC is operating and another CORDIC is going to the flushing mode, so that you can continuously get your running. So anyway, that there will be error, obviously, but that error should be in the within a limit. So if you look at here that the red color which one have introduced, the CORDIC with the repressing mechanism within this limit, some few this is error limit. Every periodically I am flushing one block and another way other around, so that within a limit I am getting my spectrums. It is not close to 1, the amplitude 100%, but some error I am getting my spectrums. So this is a tolerable limit for the spectrum analysis. Okay, so this is beauty of this repressing mechanism with the very simple logic and replicating in the one processing element. We got this problems, these issues we have resolved. So this is the maximum frequency operations, and what is the throughput what you can calculate from here with 190 nanometer technology. If you come to the different architectures what we have, see, if you look at these are the already general CORDIC CORDIC based running DFT, they have computed, they have used multipliers, memories like that, and this CORRAW, they have given CORDIC based architectures, so they have used N CORDIC and N DPRAM, okay, and N 2N plus 1 adder. But in our, but there have been the problem with the refreshing. The error is an issue. But we have introduced with our this error issues we have resolved. Refreshing we have introduced, and so that by giving the some hardware, by compromising with the hardware. So this is the hardware performance. The iterative CORDIC, we are using the 4N equivalent N stage 1 stage CORDIC, and in the pipeline we are using the M stage, one CORDIC with the M stage. Obviously we are using the more DPRAM, that is 5N minus 4M. So this is what better performance we got from our with existing in the state of art running DFT computations. Thank you. If you have any questions, I can take off. What is the time now? Yeah, 9:22. I can take 10:20. 10 minutes I have delayed.
No problem, sir. Okay, participant.
Yes, dear participant,
If yes, yes.
if you have any query, ask.
Hope I have like I understood, because online it is a big issue, and hope it will convince some basics to the some advance. I have kept open some problems. So if you have any doubts or any questions, or if you want something from me, then you feel free to ask me. I will answer your questions. Yes.
Sir, there is a question in the chat room.
Chat?
There is a question in the chat room.
Can you give me the which one?
Sir, he has written, Alpesh sir has written, good evening, sir. In one of your slide, you are comparing ripple carry adder and Han-Carlson adder.
Okay,
In our multiplier design, we use carry save adder. Is Han-Carlson adder better than the carry save adder?
Obviously. See, let me go to that slide. Han-Carlson adder is a fast prefix fast adder, so that performance obviously better than your carry select adder, carry save adder, ripple carry adder.
Sir, that much is the question in the chat box. No other question is there.
Okay, sir. Thank you, sir.
Only we are getting some thank you messages for you.
See, Han-Carlson adder is a prefix fast adder, so obviously this CORDIC architecture using very low. Now, what is the question?
The question was,
shall I go to the this mode when I like?
Is Han-Carlson adder can be better than carry save adder?
Yes. Han-Carlson adder is obviously better than the carry save adder. Any adder.
One more question is here. Can we implement this CORDIC architecture using Verilog?
Yes, we have implemented. What I have performance I have given that is implemented in Verilog STL and synthesized and prototyped on FPGA. Yes, you can do.
Okay, sir. This is the second question we seen in the chat box. This much only, sir.
So keep open. Yes.
Hello.
Yes.
Professor Roy. Uh,
Yes.
Now, that is you shown that in 2014 that you have the one work still now it is that is particularly I think the latency issue I think you resolve or you
Uh,
shorten it.
yeah,
It's like consent. Yeah.
hybrid
Yes,
CORDIC.
yes, yes.
Let me show.
Basically, we know that
Uh,
in
yeah, this
CORDIC,
one.
latency is the major issue because it is almost in a serial form. Okay,
Uh.
and so that is there. But in the recent times, there are several designs people they attempted
Hmm.
to. Yeah. So, what is the status at present? There are some what because I didn't work in the CORDIC, but I
Uh-huh.
understand CORDIC is the most fascinating component whatever in a signal processing it is used.
Yes,
CORDIC is the
yes,
most
yes.
fascinating component.
Yes, yes,
Okay,
yes, yes.
and it is for most of people to understand CORDIC, it is still it is a there's a lot of puzzle is there. Okay, and
Uh-huh.
once somebody understand the component do all the magic, you know
Yes, yes, yes,
that
yes.
is
Correct.
that
Absolutely,
I
absolutely.
understand fully. I understand,
Uh-huh.
and you tried most to make it very very simple and thing. I don't know how many participants they are carry because CORDIC is such a things. Even now physically you can explain to 2 3 times, then somebody will pick up the things.
Yes, 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 yes.
Okay, but anyway, coming to the point. So,
Uh,
what is the at in a state of the because in a recent time also still there is a over 50 years a lot of things happen, lot of
uh,
development in the CORDIC and
uh,
circuits also in the last 20 years a lot many circuits also people they proposed. So,
uh,
what
uh,
is the present because since you are working, so
uh.
what is the present status particularly on that side because
See,
wha-
thank you, man. This is very, very valid questions here. Of course, I have already told during my presentation this slide. See, if you come to the CORDIC, okay, I have given three issues, right? Uh, One is your scale factor compensation, right?
yeah,
In the range computations and in the latency. So last 52, now it is a 65 years, I think around
right,
63
right.
years, 63 years it has come up. Uh, though architecture has come off, uh, basically it picked up after 2000. So
Mm-hmm.
after 59 71 Walter has given 59 and Walter has given proposed in the 70 Walter has given only rotational CORDIC, okay,
Mm-hmm.
circular CORDIC, and Walter has given added both vector and linear and hyperbolic CORDIC.
Mm-hmm.
And after that, after 93, 92, say 90, I can say 90, some people, Vilaba group from the Spain, they started working to have resolve the issue of these scale factors.
Mm-hmm.
Okay, and also latency,
Mm-hmm.
right? Uh, so this is a CORDIC development.
Mm-hmm.
This is a development of the CORDIC issues. But this CORDICs, use of these CORDICs that picked up when the people try to replace the DSP processors,
Mm-hmm.
I mean, to implement your signal processing algorithms or image processing algorithms or your communication algorithms, to replace your DSP processor microcontrollers to a ASIC, application specific integrated circuit.
Mm-hmm.
So in the application specific integrated circuit, when it is come out, so obviously we need a hardware less hardware. So that time in application that application of CORDIC has come up in a big role, as you already pointed out, right? And you have
Mm-hmm.
know it the revolutions.
Mm-hmm.
So after that, when CORDIC has come up, when you go to the application specific, then these three issues has come up: scale factor compensation, range, limit, increase the range of your quadrant, and the latency, as I told the latency. So after that, many people have told that if you go to the computer latency, I have also pointed out what is the bottleneck for the latency. Bottleneck for the latency is your adherent subtractor.
Yeah.
and another is your iterations M. So I don't know whether that yeah. So you see, if you look at that latency or throughput, one is a adder subtractor and is a M, and number of iterations.
Iterative type of algorithm because of that.
Right. So people try to implement, now also implementing, developing the fast adders. How the fast adders can be employed in the coding so that like the latency will be increased, the critical path will be decreased, so that your computational time will be decreased, so that your throughput will increase, maintaining your iteration number of iterations. Okay. On other side, people are trying to reduce the number of iterations. So number of iterations is that how to reduce it. There are two basically people who went then basically this is Redis 2. Then people are trying to go to the Redis 2, from the Redis to the Redis 4, Redis 8, Redis 16. So people are Redis, they are increasing. Okay, Redis 2, Redis 4, Redis 8, Redis 16. Recently I have seen Redis 616 CORDIC also. Okay, but if you go to Redis development, then obviously you have to pay the hardware, but the latency will be decreased, no doubt at all.
What about the accuracy? Accuracy remain the same when you increase the Redis?
See, if you look at the accuracy point of view, accuracy exactly I cannot say, but yes, effect will be there. And see, if you look at the iterative codic, single Redis to iterative, you have to go for the M iterations, right? So obviously that some error will be there. But when you come to the Redis 4, you are reducing the n by 2, something n by 2 plus 3, something iterations you are taking care of it. Assuming that some approximation also you are taking, right, on that part. So accuracy is almost, it will remains the same, not much. There will be effect that depending upon that. Since I told now one, I have used the Taylor series. I have given one Taylor series computations. So let me go through that slide. Here I have given a Taylor series, right? I have taken the 3 terms. So 3 terms means error will be there, right? So, but the idea is that why I have taken 3 terms. After 3 terms, it does not affect my iterations. So that's why I have taken the 3 terms. But in that case, if your number of samples will be more, when bit size is more, then obviously that this Taylor series expression you have to take more. So that depends on how we are truncating Taylor series. See, if you use the 3 terms, you giving the hardware also, you are giving the hardware over here. So it is a trade-off between your accuracy and hardware. Again, it will come up. So the one direction is reducing the critical time. Another is the reducing your iteration time. As I told, as of now, the critical path reduction, people are using many research people are doing till now also. But iteration side, as of now, nobody has done.
Okay.
But after our coding. After our coding, nobody, we have published in Transaction on Computer in 2014. After that, I have not seen any coding which is challenge to our coding, this algorithm.
Okay. No,
Maybe
there are
because,
actually
see,
what? Yes, please.
tell.
No. Actually, what happened? Professor Meher and their group also they working. There are different because though I also collaborative working because many time I ask because shall I look into some codic? He told no, they're not required because you look at to some wavelet and others because my domain is that. But he having a very wider group and they contributed very significantly in the coding. Okay. And I just because I never referred any papers, but they were published. I think he has published 20 or transaction papers on codics.
Yes.
Hopefully.
Yes.
So I just thinking what are the changes they're doing so that 20 transaction paper is coming out of this
No, it
codic.
is not. See, Professor Meher published only 20 papers. But if you go to the Villalba group from the Spain, Antilo and Villalba,
Yeah.
okay, I have not given his references here.
Mhm.
Some of them Redix. एक minute. Let me. It will be there. Might be there. Let me. Redix 4. No, that references I have not given a in the
No, no,
slide.
not ISO.
There
Not
is
ISO.
called a Villalba group in
Uh-huh.
Spain. Antilo Villalba. If you type it,
Uh-huh.
since 92,
Uh-huh.
93,
Uh-huh.
they have a number of transactions on
Okay.
this development.
Oh.
Okay, and another is a Kausiki Maharatna.
Yeah, yeah, I know, I know.
Okay, so you might have heard about
Yeah,
Kausik
yeah, yeah.
Maharatna.
Yes, yes.
So Kausik Maharatna, he has done 50 years survey.
Uh-huh.
He has one publication
Yes,
that is
yes. I think that 50 years of CORDIC, Professor
Correct,
Meher
correct.
and
Okay,
Qasim
okay.
Mahato, they actually they written that paper and they have a very lot of citation on that paper.
Yeah. So what he has done, I will give you the very very magic the things. See, let me go to because you have already you are interested on it. I should tell about logic behind it. See, I was also thinking the way Professor Maharatna was thinking. Okay. In fact, Professor Maharatna is my supervisor's. This was I have done during my PhD.
Oh, oh.
No, this one, particular this initial codec.
Uh-huh.
I have started doing my PhD work. Till now, I am working. Okay, hybrid codec after my PhD. During my this job only, I have proposed that new algorithms. Uh, but here, what we have done it, I was thinking that how we can rotate it with a small angle. So suppose you are rotating V to V prime.
Right.
Okay, so you are rotating 45 degree, 26 degree, 13 degree,
Mm-hmm.
14 degrees,
Mm-hmm.
7 degree, like that you are rotating these micro rotations,
Mm-hmm.
right? These micro rotations.
Mm-hmm.
Instead of that, what I had a plan that I will define a very, a small angle, right?
Mm-hmm.
Very small resolution angle. On that step, I will go ahead to
Mm-hmm.
reach to the vector. Okay, that way I had a plan, but with the constant rotations, it is a variable rotation, right?
Mm-hmm.
But with a constant rotation, I can go to that so that I can minimize my lookup table.
Right, right.
Okay, and I will go with the very simple shifting operations.
Mm-hmm.
So that's what I had a plan, but I got it delayed. But Kausik Mahathna has published that paper.
It happens. In hardware
So
design, always it happens.
I spent 1.5 years on that to think about that thought. Only that I have not implemented. I did it in the simulations. I did it my idea. I got my simulations. But meantime, that group, they are very good. Kausin Maharatna was working, Professor Maharatna was working with a very big group.
Mm-hmm.
So they anyhow they implemented it and they validated the idea and published in a very good transaction. If you look at linear, that is what called constant scale factor. On that case, your lookup table is minimized. Not only the lookup table, your scale factor compensation. There is no need of the scale factor compensation. The title is a scale factor compensation free CORDIC architecture by Kausik Mahara. So that is one trend how to avoid the scale factor.
Uh-huh.
Okay, one is a parallel compensation. Either you do the addition and multiplications, right?
Mm.
See, for the spectrum analysis, scale factor is not an issue. But if you go for the synthesis, scale factor is a big issue.
Yeah.
So either you have to do the multiplier. If you use the multiplier divider, again the idea of the CORDIC is gone.
Gone. Right.
And if you replace with your linear multiplier divider with your CORDIC, then you have to use another CORDIC for that. How do you have to add it? So
Overhead.
latency
Yeah,
have
you
to
have to
include
add some overhead.
overhead. That's why
Ah.
that parallel compensation has come up.
And along with that, more codec means there is some always a error is
Error,
introduced.
error introduced.
Right.
Then parallel CORDIC has come up.
Ah.
So people has given thought to the scale factor side, your latency side. Still it is open. Like, can we do our CORDIC algorithms within a few cycles, maybe 2 to 3 cycles? Then that will be any saving in one iteration will be a transaction paper here. If somebody will work and challenge, it reduce one cycle compared to our architecture, that will be a transaction. I'm sure. But the thing that we supposed to work, but means so I have diverted to the other domain. So
That
domain means
exactly.
I'm using this CORDIC, but application side I'm using. Communication signal processing side I'm using. So I'm using but the development of the CORDIC I'm not doing it at present. But application of the CORDIC I'm doing.
Okay, okay. Very nice, Professor Roy, listening to you. And at least, I try to read the Codic, but after, 3, 4 pages or something like that, I always leave that, yeah. But in today's lecture, it appeared to be very, very, attractive for me.
Thank you.
Okay.
What's your name? I am not able to see. No. You are?
My name?
Tell. Sorry. Actually, I have not used my. Let me go to full window. Then I can realize. I'm not. Yeah, Professor Mahanti.
Yeah, yeah.
This is the problem with the online, na?
No issue. Okay. Prabir?
Yes,
Yes,
any
sir.
more questions?
Any more questions from the student side and participants, not student faculty side?
There are no question. Further question.
I think there's no more questions. Now, thank you, sir, for such a beautiful presentation and quality lecture in which you covered all the advanced DSP in very short duration and limitation of FT, DFT, FFT, and issue of leakage due to direct connection of bulk of data. And suggestion about product is being employed to design window and running the design of product and specification to design and design windowing architecture and running DFT architecture. Once again, I would like to say thank you, sir, for accepting our invitation for this FDP and give us your valuable time. Thank you, sir. Thank you so much. Hello. Now I think we should conclude our session, today's session, and I request to all the participants, please join us tomorrow at 7 p.m. And for tomorrow sessions, Professor Kamlakant Mahapatra is our resource person. He's from NIT Rourkela. So thank you.
Okay, Professor
everyone,
Roy.
and
Thank
good
you.
night, all of you.
Hello.
Yeah, thank you, Professor Mahanti,
Uh,
for your invitations.
and we'll try to catch you some other time.
Sure, I am always available. Maybe you
And
change your theme. I will talk about my latest
let me
research
know if
topics.
when we are coming to Odisha or this side. Let me know. We find some time to meet.
See, every 1 month, 2 months, I'm going to Bhubaneswar,
Uh-huh.
and
Then you can plan. So at least you can plan to just you can come this side and just move away.
sure, you see, go means you arrange another functions, another talk, another presentation,
Sure,
another
sure,
workshop
sure,
kind of
sure.
stuff.
So that
We
that
will
that
make it
always
because
that always.
see, Sambalpur is like my Bulla is my like home. All friends are there in Bulla,
Yeah.
and Sambalpur also one of what is his name? Barpanda is there. I know him very well.
He is with us now.
He's today he's there or not?
No, he is not there, I think, but
Hmm.
he is with us.
So many friends are there in Bulla and Lono, you see Bulla. So you make some good. So call the Meher sir. Okay.
No, he was actually in the day one. He was the resource person. He started
Yeah.
the ball rolling in the day one, and actually he's supposed to come in the physical session also. But earlier he was planning to go to actually travel to Germany.
Okay.
Okay, his younger son is there, so that's why he told that you put me on the day one so that I can able to travel. So, but because of some reason, I think he's not going or he's postponed. Actually, I don't know